Just so you know, I'm a storage guy. I'm not a networking guy. So anything that you see erroneous, it's not my fault. Um, the other thing I apologize for, as you can tell by the title that was just read off, which is different than this, I tend to be very verbose with bullets and things like that versus pictures. I tend to produce the content so someone can follow along without me narrating. So, if it looks a little busy, that's why. And again, it's not my fault. I have issues. All right. So I'll lead it off. There's a series of these little things versus bullets that I like to start off with. And I want you guys thinking about, as we move towards 5G edge computing, what do we have to do really differently from the perspective of storage architecture? You'll hear a lot about core networking, you'll hear a lot about edge networking, you'll hear about packet processing. But at the end of the day, again, I'm a storage guy, so I want you to think about how you incorporate storage to make all of that happen, especially when you have to persist data. While you're at it, what can you do with your storage if you can actually orchestrate your storage and do service function chaining and things like that, whether it's with Cord or other pieces of software that we're developing in Cloud Native, developing in ONAP or other places, if your storage were kind of more intelligent. And what would you do, if we could significantly reduce, things like backhaul, latency, CapEx, and OpEx, but again, from a storage perspective? All right, this is kind of the forgotten component in the triad of major things that we have to take into consideration. So I'm going to be talking about that and looking at how we can actually reduce total cost of ownership. So when we think about reducing TCO and CapEx and OpEx, think in your head, what's a good number to reduce things by? I had one that was tossed out at me a little while ago, which was, look, got to drive a 50% reduction in CapEx and OpEx to sustain 5G. I thought, holy cow, that's pretty major. We've been trying to do that for the 30 years I've been in the storage industry, and everything keeps going up. So I took it as quite the challenge. Well, when we're talking about our storage, let's start with a few things that we might want to accomplish. Some of you might want to actually persist data. You can talk all day long about hundreds of millions of packets per second. Go ahead and try doing that, though, when you actually have to read from disks or write to disks. It's a lot more challenging. We might want to reduce costs as we're rolling out or, thinking about our storage architecture. Reduce power, kind of a good thing, right? Some of you might be energy conscious. Reduce latency, heard a lot about latency so far this week. What if we could go ahead and reduce backhaul from a storage standpoint, if that could contribute towards that reduction? Yeah, okay, let's add that in there. So what we end up with is all these are good ideas, good design goals for architecting our storage solution. Let's talk about persistent data. We have two types typically, structured and unstructured, and if you can think of a third type, tell me about it later, but I find that two buckets have been pretty good for the past couple decades. So let's talk about what's structured data. Well, it's the data that's in a database. It can be handled with simple queries, right? Forget about the locality thing. Just think of it this way, right? If data's in one location and the thing with the brains that's making the query for the data is another location, it might contribute towards latency and things like that. All right. So, how do we go ahead and reduce all those things when it comes to structured data? Okay. Let's take a look at unstructured data. What's unstructured data? We're talking about files. What kind of files? Videos, pictures, logs, whatever. Right. It's massive. It grows by petabytes per day, as reported by some of the operators that are here at this conference. We don't really I haven't found one operator that has sized up what the impact of unstructured data is at the edge yet. Okay? We're dealing with it bad enough at a data center level. All right? Also, when you think about dealing with unstructured data, just something to bear in mind, it's sometimes hard to put a 2U rack enclosure on top of a light pole. So I know that some folks are trying to figure out new types of access and things like that, but that's a design challenge to bear in mind as we progress through this presentation. So with those things in mind, how can we reduce our storage costs? So as a prelude to that, let's look at a couple of architectural comparisons. The first is a centralized approach to storage. What I mean by a centralized approach to storage is the CPU is central to the disks. In other words, we have one CPU and we string a whole bunch of disks behind it. It's a 20-year-old architecture. That probably goes later than that, but if you look at all the network architectures out there, network storage architectures, they're all based on this approach. All right, it doesn't matter what the file system is, doesn't matter if you're using NFS, CIFS, if you're using Ceph, if you're using Swift. All right, it's hard to balance the I/O. This is not a slam against any CPU manufacturers, but the CPU is almost always the bottleneck. It's simple amortization. The faster I make the processor, the more inclined I am to add more NIC or more storage to the back end to kind of amortize the costs of that shared expense. And next thing I know, the CPU is the bottleneck. You give me a faster CPU, I'm going to add more networking, more storage. CPU is the bottleneck again. Just trust me on this. I've been doing this for a long time. The current packaging tends to be expensive to scale and to operate. Again, this is in general, especially when we're talking about the edge. The other thing is the whole unit, the whole enclosure, all the drives in that one CPU complex, that is the object storage device. All right, so if I want to do any kind of resiliency, clustering, and things like that, I've got to have several of these or deal with a single point of failure. The other approach to this is a decentralized CPU approach to storage, where I'm basically combining a CPU and a disk together to form a pair. All right, that's my unit. A 1-to-1-to-1 kind of ratio, right? NIC, CPU, and disk. Forget about how, if we think about, the disk in terms of if it's got a SATA type of interface on it, okay, anything more than really gigabit Ethernet on the front end of that disk is probably overkill. If it's got an NVMe type of drive on the back end, then we probably want to have a 10 gig interface. Any less than that, we're not utilizing that SSD very well. So think of it in those kind of terms, and what you'll find is the whole unit is the bottleneck. That could sound bad, or you could think about it as, well, I've got this one physical unit. It's good for this amount of I/O. If I add another one, I just doubled that. If I add another one, I just doubled that. So is it such a bad thing that one unit is a bottleneck? I don't think so. As I go along further, I'm going to show you that packaging becomes a lot less expensive when you think about storage in that kind of a fashion, and we can drive as much as a 10x reduction. That's a lot more than 50% for those that weren't math majors. I was a math major, so, but it didn't do me very well. By the way, each one of these CPU disk pairs is an object storage device. So again, instead of treating a whole chassis as one object storage device, I can treat each unit as an OSD. I can do my clustering inside of a box. I can make lots of clusters inside of a box or certainly within a rack. So let's start looking at some costs if we do this. And this is a little bit counterintuitive, right? I mean, if I add more CPUs versus sharing a CPU, my cost might actually go down, not up. It was counterintuitive for me, all right? And I couldn't do this 10 years ago. I could start to do it 5 years ago with 32-bit CPUs. I can definitely do it now with 64-bit CPUs. But if I start taking some of the shared components like chassis, motherboard, CPU, NICs, and stuff for a shared architecture that we just went over, I'm looking at basically ascribing $167 per disk. Now, you'll get the slides and everything, and you can follow the link, and you can go ahead and do the math yourself, but just trust me, my calculator said it was $167. All right. If I take the decentralized approach, then I get a different number. I get $41.50 per disk. All right, so that's the tax, the shared tax. That's only 4x difference. I promised you guys a lot more. But bear in mind, with the shared architecture, the entire enclosure is an object storage device. So if I want to go ahead and create resiliency, I've got to have 3 of those. Now I'm at a 12x difference in cost. Let's look at it from a power perspective. All right, there's a lot of things that go into this, such as how big of a system do I want to go ahead and build? The typical rule of thumb is the more components I add, the more power it consumes. All right, what type of disk am I using? If I'm using an NVMe disk, non-volatile memory express, that basically means a disk that connects up through PCIe, and it's got a number of latency benefits associated with it. One of the downsides of that is, they're really fast, but I'm looking at 25 watts per drive. If I look at a 5400 RPM disk, that's about 2 watts per drive, just to throw it into comparison. And if I'm looking at, a SATA-based SSD, that's roughly 4 watts. All right, so now what kind of CPU are we using? That's another thing that we have to look at. A 64-bit ARM CPU runs as little as 1 watt, whereas an Intel CPU can also run low, but not typically that low because we're typically using them to do different functions and stuff, so they're packaged differently. It's not their fault, it's what the consumer and folks are asking for. All right? If we just look at the drive choices, forget about everything else, and just look at the power consumption from a drive perspective on a 24 drive type of model again, we're looking at 24 7200 RPM drives, 240 watts, 24 NVMe disks, 600 watts, okay? And again, we're not including anything with CPU, motherboard, and shared electronics. So our reference design that we've been showing folks based on the 24 nodes, so 24 servers with 2 gigabytes of memory each, 4 processing cores, 2 GPU cores each, and 24 5 terabyte rotating disks, that whole thing operates at about 100 watts, kind of like a light bulb. That's when I kind of had my aha moment that maybe we're onto something. But let's talk about latency and backhaul. At Mobile World Congress, I was asked, well, if you had some kind of a re-architected storage that had processors all over the place, could you do something with it other than just store data? So at Mobile World Congress, came up with the demo. This was a single drive demo, single 5400 RPM drive, and came up with a face recognition application. Basically, the server just served up a simple JavaScript app that controlled the camera and then created a persistent WebSocket back down to the drive where we captured it. That triggered a couple of neural networks that were running on a Mali GPU. All right. That GPU did a couple of functions. The end result of that was a 4 megabyte image was rendered as a 200 byte vector that represented 256 key identifiers of a face. That 200 bytes, not the 4 megabytes, but the 200 bytes was then sent to the index server to be matched. All right? So that was a considerable reduction in backhaul. All right? And the time to go ahead and render all that was 10 milliseconds. All right? That's what we could do with just one drive. 10 millisecond face recognition, a 20,000 to 1 reduction in backhaul for the augmented reality portion of it. At ONS, we took this kind of demonstration, beefed it up a little bit, took it to 200,000 to 1. So we can improve upon it considerably. We did this again, and we continued to shrink the number of Mali GPU cores for the object detection as we moved along. What we found was the CPU cores were pretty freed up. We were using less than 5% of the CPU. So that left a lot of opportunity to use those CPUs for other functions. It's highly scalable in design. So now take that, right? So we're dealing with a significant reduction in power, a significant reduction in costs. Now, what if we could go ahead and make it in, do things like orchestrate, do service function chaining, things like that? How would we benefit at the edge? We could take an augmented reality function and direct it towards a specific drive if we wanted to, not towards a specific box. All right, so we can gain quite a bit of granularity. If a device, think of a cell in an organism, fails, we can redirect it to another device within the same body pretty efficiently, just using just simple software-defined rules. We have folks talking to us who have liked the design enough down in the ARM booth that now they're talking about taking the packet core and driving that onto each drive. Think about what that means. Things like real-time DPI on your packet core, all hardware offloaded. Okay, so what we end up with, and these are just some of the other things that we've been doing. We've got a 42-node 1U out there, so 42 disks, 42 CPUs in 1U, showcasing all this in the ARM booth, running ONS, running OpenFlow on every single drive, and doing single sign-on that's based off of just face recognition. We're doing that in conjunction with Orange. So, wrapping it up, what are some of the other use cases that we've done with this that we're working on with this design? Virtual CDN. Not virtual CDN supplying content to the edge, but virtual CDN supplying content from the edge, which is a difference, right? Because if you go downstairs, you'll see that we've been able to do quite a bit of this, high performance and computing, along with the storage part, and shrink it down into a board at 20 watts. We can shrink it down even further in terms of power consumption. Lots of things we can do with that. Real-time object classification of video content, we're doing that. We're showing telco in a box downstairs with the full MCord 6 stack, running on as little as 1 gigabyte of memory. Okay, so if you wanted to do cord in a box but didn't have a box with 48 gigabytes of memory and a minimum of 32 cores, come to us, we'll get you up and running, and we'll do it all within a gigabyte. Okay, so all of this is running at less than 200 watts. We're doing the face-based single sign-on as a VNF on that MCord fabric. We're coming up with more examples every day. We've had several just in the last couple of days come to us as new use case POC opportunities that we'll begin working on. What are some other things we're doing? We've already talked about more and more machine learning, right? Creating more transparency or seamlessness between ARM compute library models based on TensorFlow or Caffe, and making that a lot more seamless. So if you've got IP already built up on top of CUDA, on top of AMD's GPUs, on top of Mali, and you're trying to find a way to converge all of that, we can help you with that. Just come down the booth, grab a card, let's have a discussion. If anybody watches Silicon Valley, this was kind of a joke, but not so much a joke when you start talking about putting storage and computing at the edge with such low power. Okay, why do we really want to centralize any other functions? Well, I mean, there might be some, but if you can start doing it at the edge at lower costs, why won't you? We figured out, based off this architecture, how we can put 4,032 servers and 8 petabytes in a single 72-inch rack. We can do that right now. Okay, fathom that. These aren't just little single-core, 32-bit or 8-bit computers. These are quad-core, 64-bit computers, dual GPU cores per computer node, and 2 gigabytes of memory. Okay, it's not your standard architecture, but it's pretty scalable, and we believe that we have the ability that by the really about the next summer, to increase this up to 10,000 servers and disks in a single rack. All right. We believe face identification is critical for everything from national security, personal security, to improve customer service. We're working with operators who, think that you should no longer have to hand out a loyalty card to get your discounts and service, but that just by walking into the store, the staff can identify you and identify whether or not you're entitled to discounts and everything right from the get-go. We're actually demonstrating that downstairs. Okay? It's not necessarily a Minority Report anymore. So with all those things, how many terabytes, petabytes, or even exabytes of archived data are you currently sitting on? What if you could go ahead and reduce that CapEx by greater than 10x, just using it just for storage? Forget the CPUs. Forget there's any GPUs. If I could tell you today that you can reduce your storage costs by 50%, most of you would say, I got to look into that. I'm showing you a design downstairs where you can reduce the costs and the operational cost, power consumption, tenfold. That's significant. You want to talk about edge computing? You want to talk about scalability? It starts with this. If you're not dealing with storage, then you're not thinking about the edge properly. What if you could categorize that, those petabytes of data in such a way that, it's all of it's unstructured, but now I look back over a 5-year block and I realize, we generated thousands of reports between these years on the feasibility of open source software in our corporate environment. What could that do for you, right? How much more categorization could you go ahead and do? How much classification could you do on petabytes? And you're not even passing it to a server to do it. You're processing this right on the storage that's housing and protecting and serving up that data at lower cost. It's kind of like a free service. All right? I think that's intelligent design. Well, in short, we believe that a new architecture is deserved. Everything we're doing is open source, open hardware, commercial off the shelf for the reference designs and everything. We don't want any vendor lock-in for any of it. Oh, and there's no membership fee. Just because we haven't yet disclosed a use case doesn't mean it doesn't exist or isn't applicable. New stuff is coming up every single day that we're dealing with. With our march towards 5G, I believe we must reduce power. If you're not using machine learning with your data, your new data or your archive data, I hope that you'll reconsider that and start incorporating it. You may not know how to incorporate it. Stop by, grab a card, let's talk. If you're not sure how to do it, we have a team of folks who will do it for you. Okay, let's make use of all the data that we've already generated. And then lastly, before you leave, what would you do with 10,000 servers and drives in a rack at 10x reduction in power and costs? Would you do things differently in your edge plans? Okay. I think that the drive is the computer for 5G edge. I'm happy to be proven wrong, but anyway, that's what I have, and I appreciate your time. If there's any questions, I don't even know if I have any. I've got 5 minutes. How did that happen? Any questions? No questions. I'm done early. Thank you.